Welcome to The Explainer. Today, we are going to unlock the mystery of how artificial intelligence actually processes information. If you've ever felt like AI is just this massive, totally incomprehensible black box doing magic tricks behind a curtain, well, you are definitely in the right place. We're going to pull that curtain back. We'll follow the actual journey of a single data point as it travels through a neural network, turning what feels like pure magic into really clear, understandable mechanics. So, let's dive into this by asking the absolute biggest question everyone has when they first hear about neural networks. How does a machine actually think? We use that word constantly, right? We say the AI is thinking or deciding. But computers don't have brains. They have silicon, circuits, and code. To really grasp what's going on, we have to fundamentally shift our perspective on what programming a computer actually means.
Think about traditional programming for a second, the stuff that runs everything from your calculator to older video games. In that world, the human does all the heavy lifting. We write exact, rigid rules, plug in data, and the computer just calculates the answers. But neural networks? They completely flip this upside down. It's a total game changer. Instead of giving a computer rigid rules, we give it a massive amount of data and the correct answers, and the network learns the rules all by itself. We're no longer dictating the how, we're just providing the what, and letting the machine bridge the gap.
To see exactly how it learns those rules, here is our roadmap. Number 1, inside the AI black box. Number 2, meet the artificial neuron. Number 3, weights, biases, and math. Number 4, through the hidden layers. And finally, number 5, making the final decision.
Section 1. Inside the AI black box, finding fluid patterns.
Let's start with the problem that makes neural networks so incredibly necessary in the first place. Traditional programming completely falls apart when you try to identify something as nuanced and variable as human handwriting or the complex contents of a photograph. Just think about it. If you try to write a strict rule to identify the number 8, how do you account for a messy loop, an unclosed top, or a slanted line? You'd have to write literally a million different if-then statements to account for every single way a person might scribble an 8, and honestly, you'd still fail. The real world is messy. It's full of complex, fluid patterns that completely defy simple rules. And this is exactly where our neural network steps in to save the day.
Section 2. Artificial neuron, the building blocks.
To understand how the network solves this messy real-world problem, we first have to meet its foundational pieces. Now, I know the word neuron makes us think of a squishy biological brain cell, but actually, scratch that. Don't let the biological terminology confuse you. In a digital network, an artificial neuron is simply a tiny mathematical container holding a specific number. That's the whole shebang. It holds a single piece of data, and its entire job is to eventually pass that information forward to the next layer. It's way less like a biological cell and much more like a bucket holding a very specific amount of water.
Section 3. Weights and biases, filtering the signal.
So, how do all of these individual containers actually talk to each other to make sense of our messy handwriting? Imagine a single activation number lighting up inside a neuron, let's say 0.85. This number represents a tiny piece of our raw data. If we're processing an image, this number might represent how bright one specific pixel is, just waiting to be passed to the next layer. A high number means the pixel is super bright. A low number near 0 means it's dark. But this neuron doesn't just indiscriminately blast its 0.85 value forward. That information absolutely has to be filtered.
And here's where it gets really interesting. The connections between neurons have weights. Think of it this way. If the neuron is the light bulb, the weight is the dimmer switch. As that 0.85 value travels down a connection path, the weight acts exactly like a dimmer switch, dictating how powerfully the next neuron in the chain should shine. A high weight cranks up the signal, meaning this specific connection is super important. A low weight dims the signal down, essentially saying, hey, ignore this data, it's not relevant. To really lock this concept in, imagine this math like a committee voting on a decision. The weights, those measure how much we trust a specific committee member's expertise. If we're trying to identify a dog, and one neuron is an expert at identifying fur, we give that neuron's connection a really high weight. We trust its vote. Biases, on the other hand, represent a node's baseline hesitation before they even raise their hand to vote. A high bias means that neuron is incredibly stubborn. It needs a massive amount of incoming signals before it decides to actually activate and pass a message forward. So as our data point moves, it's constantly being multiplied by weights based on trust and adjusted by biases based on how stubborn the next neuron is.
Section 4. Hidden layers, forward propagation.
Let's see how this builds as our data point leaves the input layer. Through a process called forward propagation, each successive hidden layer extracts increasingly complex patterns. Our data doesn't just instantly jump from a raw pixel to a final answer. It takes steps. In step 1, the very first hidden layers are just looking for basic edges and lines, simple light and dark contrasts. But as those neurons pass their weighted votes forward to step 2, the next layer combines those edges to detect shapes, circles, ovals, triangles. Then, those shape-detecting neurons vote and pass their signals forward to step 3, where the network combines them to detect something incredibly complex, like a human face or a specific animal. It's a pretty remarkable cascade, piecing together simple lines into fully formed concepts, layer by layer, vote by vote.
Section 5. Final decision. Calculating probability.
After surviving the gauntlet of math, weights, biases, and all that tiered pattern recognition, our process data arrives at the output layer to finally give us an answer. At this stage, the network has crunched literally millions of tiny committee votes across all its hidden layers. Every single edge, shape, and pattern has been weighted and tallied. It's narrowed everything down to these final contenders. The network isn't just bluntly saying dog or cat. It is doing something way more sophisticated. It's presenting the final probabilities for each possible category it was trained to recognize.
And here is the ultimate payoff of our journey. 85% sure it's a dog, 15% sure it's a cat. The neural network isn't just randomly guessing, and it sure isn't experiencing a gut feeling. It is providing a highly calculated probability based on the very specific math we just explored. The edges it detected, the shapes it formed, the weights that amplified the fur experts, and the biases that held back the false signals, all of that mathematically culminated in this exact 85% output. The black box is actually just a remarkably transparent series of mathematical filters, all working together in perfect harmony to make sense of a really messy world.
So, as we wrap up the explainer today, I'm going to leave you with this final thought to ponder. We've seen exactly how the machine takes data, weights it, passes it through hidden layers, and makes a decision. But remember our very first point? Neural networks learn the rules based on the data we give them. So if the machine's entire system of weights and biases is shaped solely by its training material, who decides what data it learns from in the first place? The math inside the machine is beautifully objective, for sure, but the data we feed it, that is intrinsically human. Think about that the next time an AI processes an answer for you. See you in the next explainer.